Hi, I'm Ken Goodman, and this is Electron Stance. What I have for you this time is yet another impractical repair. This time, it's our old cordless vacuum cleaner that bit the dust. Much like my old wall beard trimmer, the battery pack just got to the point where it wouldn't hold a charge. At first glance, this looks like a replay of the beard trimmer repair, but there is one really big difference. The battery pack voltage is much higher, so there's a correspondingly larger number of cells. Because of the larger cell count, I was unable to find an off-the-shelf single-chip charging solution. So this time I plan to use a microcontroller IC to control the charging. That means there will be a firmware development task in addition to the circuit design and PCB design. I got a deal on some nickel metal hydride packs that add up to about the same capacity, but I'm not sure they have the current capacity to run this blower, so I'm just going to give it a quick spin. This is not a very good test of the capacity of these batteries, but it'll give me some idea of whether they can run this vacuum. Okay, seems okay at a glance. So I'll proceed with building a charger for these guys to replace this board. Now I need to draw a schematic for the new charging board to replace this one. The schematic for the trimmer setup is a convenient starting place since the function and organization are somewhat similar. So I've made a copy and will go through and modify it here and there. The charging voltage and current are different, so let's document that. The charging circuit itself will be totally different, so I'll start deleting stuff in that block and add a small block showing the external LED indicator, which I will reuse. The motor and switch wiring are different, so let's update that and the connections to the new board. Since I'm using two battery packs with connectors attached, let's add separate connections for them on the new board for convenience. Now I'm stuffing a microcontroller-based charging circuit into the old block on the schematic. I could expand it and make the schematic a little nicer and easier to read, but sorry, I'm skipping that bit. The basic idea here is that the microcontroller will sense the battery voltage, decide how fast to charge it, then turn a MOSFET on and off as needed to make that happen. We'll use an I/O pin with PWM available and set the frequency and duty cycle in software. The external LED will indicate charging status, probably just blinking while charging, then on when done. This charger should work fine as shown with just a current limiting resistor R4 between the switching MOSFET and the battery. But that would waste a good bit of energy during charge. So let's use series inductor L1 instead, with flyback diode D3 added to keep charging current circulating during MOSFET off times. We can always go back and use R4 in place of L1 if we want to for some reason. This is not a very complicated design, but there are still a lot of details to consider, which is part of what makes this such an impractical repair, right? Just as an example, consider our battery voltage sensing. I'm using a resistive voltage divider to scale the max charging voltage down to something under our VDD supply voltage. That means we're always draining the battery slightly when not in use or charging. We can use large resistances to lessen the drain, but that gives a large source resistance going into the A to D pin on the processor, which increases measurement errors. Smaller resistances will improve accuracy but drain the battery faster. If this trade-off were a problem here, we could add a series MOSFET which would be off when not connected to a charging source. In this case, I'm trying some fairly high resistances, making the current drain pretty small compared to the battery size. The equivalent source resistance is higher than recommended for our chip, But when I do the math, the A to D's leakage current in or out of that source only adds about 0.02% error typically, or about 0.5% in the worst case. This seems like a good time to fess up that my design process rarely proceeds smoothly, e.g. from concept to schematic to PCB to firmware to finish line. Usually I get to this point knowing I haven't thought of everything. So in later stages, I will keep coming back to check my work and worry about what I might have missed, tweaking the schematic as I work on the board layout, for example, and even making hardware changes as I work on firmware and test the prototype.
For this project, I'll start the board layout by drawing the outline, since we know it needs to match the dimensions of the old board. No mounting holes are needed since the board fits in a slot in the housing. The next step will be to make sure we have appropriate footprints selected for every component on the schematic, all through-hole parts for an easy build. Note that some parts on the schematic are external to the PCB, so the footprints for those can be blank. Then we can load the components from the schematic into the PCB editor, keeping in mind that we can review and change component footprints right up until the time we order blank boards. Now let's move components around so they fit inside the board outline and try to place them well relative to each other so routing the connections won't be difficult. Oops! What the heck are those surface mount resistors doing there? Let's fix that before going any further. After moving things around a bit, I'm looking at a decent component placement. Notice the unrouted connections display, or routes nest, doesn't show a lot of connections crossing each other, so routing should be pretty easy. Reviewing the components and placement, I do see several minor changes I want to make. For instance, it would be nice to use the same footprint for Q2 and U1 since they're both in TO92 packages. I'll leave some things unchanged even though they bug me, since this is for a quick one-off build, not real production. The main switching MOSFET, Q1, is a beefy TO220 part, which is overkill, but there's room for it, so I'll leave it alone. I'll probably build the board with shrouded headers for the battery connections, but rather than showing those on the schematic, I'll just place the independent pads the proper distance apart so the appropriate headers will fit. So here's a parts placement I'm satisfied with. And now it's time to lay down some actual traces to convert the rat's nest to physical connections. Here's a board layout with everything connected. And along the way I fixed a couple of minor oversights, like adding a pad for connection to the external switch. Before ordering boards, let's look everything over and add some things like identification, instructions, extra legends, and the like. I don't think we need heat sinking on anything, and I'm not worried about EMI for this one-off gizmo at home. Here is the finished layout. Time to order prototype boards. I'll use OshPark for this project, so I won't bother with Gerber or drill files since OshPark can import the KiCad files directly. There are several parts I don't have on hand, so I'll order them from DigiKey. They'll doubtless get here long before the PCBs.
One little detail with these OshPark boards and similar services where they panelize a bunch of unrelated designs together for fabrication. They use these tabs to connect your board to the neighboring boards, and a lot of the time those get in the way and they need to be removed. And usually that's good enough. Oh, and let me say, as I've said many times, it is so much easier to build prototypes with through-hole boards than surface mount. So here's the completed board. There are a few pads where wires will get soldered directly on when I install it in the case. For now, I've got charge input wires connected for development and test. I've got the external LED on its little carrier board with its lead soldered directly to the board, and that LED is going to be my only feedback from the processor unless I decide to use the Picket debug capabilities, which I probably won't.
Time to write some firmware to make this board do what we need it to. I'm using a processor I'm fairly familiar with, so I can borrow bits and pieces of code from old projects. Usually the first thing I do is define the I/O pins that I'm using. So let's look at the schematic and add some I/O definitions to match. The software task here is fairly simple, I think, so I'm not going to set up a timer interrupt service routine. I'm just going to check the timer flag in the main loop and keep time in the main loop along with everything else. Now, the first thing I want to do is write a little simple Hello World app. In this case, that just means blinking the LED to show we're in control of the hardware.
Okay, so I plugged my old Picket 4 device programmer onto the programming header of my target board, programmed my 5 Hz blinky, and there's my Hello World blinking LED. To make good use of this blinking LED, I'm writing a routine to blink out a general 3-digit number, including 0 digits. A lot of the time, similar controls will blink out error codes or status codes that don't include zeros, and that certainly makes things a lot simpler. To support my 0 digits, I'm adding a marker at the beginning of each digit. So 2 markers with nothing in between will be a 0. So here I'm blinking out an arbitrary value of 218 to test my 3-digit blink format. "218." Did you catch that?
Now that I can blink out an arbitrary number, I want to show the battery voltage there. So I have to read it first with the A to D converter in the microcontroller chip. But looking at the data sheet for the chip, I see it has a 4.096 volt precision reference internal. It would be great to use that as the voltage reference for all my A to D conversions instead of the approximately 5 volt reference on the power supply pin. Now I could read the battery voltage and read the 4.096 volt reference, both based on the approximate 5 volt reference, and then do the math to correct the battery voltage reading. But it'd be much better just to read the battery voltage directly using the precision reference. The problem with that is my voltage divider circuit on the board puts out too much voltage. So I think it would be a good idea to go back and tweak the design a little bit to adjust the resistor values in the voltage divider circuit so that my useful range of battery voltage during charging even is within the 4.096 volt reference. Let's do that. I could buy some different resistor values and wait for them to show up and then make this change, but I'd much rather go ahead and use what I have on hand. So that means I might add some series or parallel resistance in the circuit to one or both of those resistors that are already on the board. So let's take a look and see what my options are with this spreadsheet. It turns out I can use the original resistor values in combination in a couple of different ways. I can either put B in series with A, or I can put A in parallel with B. And it was surprising to me at first that both of those worked out to the same ratio, but it shouldn't have been. When I do the math, I see it's guaranteed to work out that way. Well, it's easier to put a resistor in parallel with one of the parts already on the board. So that's what I'm going to do. I'm going to put a second 549K resistor in parallel with my 187K at the bottom of the voltage divider. And here's a look at the board that I've modified in that way. So now that I've got a good voltage divider set up, let's actually write some code and read the A to D, calculate the battery voltage, and blink it out so that I can see how well that's going to work. God, this code is horrible. There's no filtering added. I've got a 0.1 mic on the input of the chip where the voltage comes into the A to D pin. So this might not work out too bad. If there's too much noise, I'll just add some software filtering, no problem. But let's take the simple approach and test it first. Here I have my charging board powered by my bench supply. I've got the batteries connected to the board. They're currently sitting at about 15.3 volts or so. Let's see what the board is measuring. Okay, there's the first digit marker. There's a 1. There's the next digit marker. There's a 5. There's the last digit marker. There's a 3. It's measuring 15.3 volts, the processor is. Not too bad. We'll live with that. The last hardware feature I need to check out before I start charging the batteries is my PWM output. I've added initialization of the PWM peripheral at the top of main. I've added a simple function to set the PWM duty cycle that I can call from main. And down at the bottom of my main loop, I've added a test ramp where I'm just changing the PWM duty 10 times a second, just so that I can see that on the scope. Here I'm powering my charging board from benchtop supply. I'm looking at the PWM output pin on the scope, and I've got a test LED on the output just so that I can visually see that ramp. So PWM channel's working and under my control. On to the final firmware step. Here's another little hiccup. When I was checking out my PWM output, I noticed first of all that I was overdriving the gate of the large MOSFET. And second, that it was a bit slow to turn off at 10 kilohertz. So I'm modifying the gate circuit as shown here. Now I'm adding a fairly simple-minded charging algorithm to my program. I think I can get away with this because I'm using nickel metal hydride cells
and they're pretty rugged. They're pretty safe, and they can tolerate a lot of different charging methods. This algorithm is certainly not ready for prime time, but I will test it here in my one-off home application and modify it if I really need to. I will give you a brief description of my charging algorithm though. I'm going to start with the charging output off, measure the battery voltage for about 1 second, and if the voltage is too low, it's a dead pack. I'm not going to try to charge it, I'll just go to an error state. If it's already high, I will just go to the full state and leave the output off and monitor the voltage until it drops a bit. If it's in the normal range, I'll start by charging either at a low rate for a deeply discharged battery, a high rate for bulk charging in the middle, and dropping back to a low rate as I'm approaching the full voltage. If I charge for several hours and haven't reached the full state yet, I'm going to time out. And I'm not going to show that as an error state, but I'll go to a timeout state and hold there. So on the LED, a fast blink will indicate an error. A slow blink will indicate a timeout. The LED will be on steady to show the end of charge. And while I'm actually charging the battery, I will blink out the latest measured battery voltage.
Here's a short benchtop charging test in the bulk charging state. One detail I forgot to mention before is that I'll charge for about 10 seconds, stop charging for about a second to measure the voltage and then decide what to do next. Now it's time to cram everything back into the housing, give the vacuum a quick test, and put it in the charging cradle. Here the vacuum cleaner is sitting on its charging cradle. It's in the bulk charging state. And if you watch for several seconds, you can see it's reading out 15.8 volts on the battery. So, was this a successful repair? I'll have to use the vacuum for a while and see if the battery pack holds up. Was it worth the effort? Well, it was for me, but that's just because I'm a retired old coot, and I have the luxury of being able to spend a lot of time on a project like this. Take care.